Today's lecture will be on the excess ion calculation. This is building upon the idea in the previous lecture of the titration problem. Titration problems are often done so that you can determine an equivalence point or an endpoint of a titration. We use a burette and deliver a very small amount of acid or base so that we can achieve that equivalence point. Now, as chemists, we are doing something a little bit differently. What we're doing is mixing a certain amount of acid with a certain amount of base. Volumes and concentrations will differ with each problem. The odds of getting the equivalence point when we choose an arbitrary amount of acid and base to mix together is not very likely. Therefore, we're going to end up with either an excess of hydrogen ions or an excess of hydroxide ions in our solution. We have 5 steps for completing this problem. As you can see up on the screen right now, we will complete steps 1 through 5 with the example found on the second page here. We have 35 milliliters of nitric acid, 0.300 molar, as added to 350 milliliters of 0.800 molar sodium hydroxide. We'd like to know what the excess of hydrogen ion or hydroxide ion concentration is after the neutralization reaction occurs. So we need to have several chemical reactions written up on the board. The first one that we need is the neutralization reaction that will occur between these two species. We have nitric acid, which is a strong acid, combined together with sodium hydroxide, a strong base. That will form water, and we will form an ionic compound, sodium nitrate. The next thing that we need to have is, because we're dealing with both a strong acid and a strong base, we need to have their ionization reactions written. We have HNO3 ionizes 100% to form hydrogen ions and nitrate ions. And then lastly, we will have our sodium hydroxide reaction, which will produce sodium ions and hydroxide ions. We'll use both of those molar ratios in our monorails here shortly. That is step 1 from our process that we have on this slide here. Step 2, we're going to solve for the moles of H positive. We have 35 milliliters of the HNO3. That's going to be the starting point of this monorail. We will first get ourselves onto the mole map by converting from milliliters to liters. Then we will move from the bottom of the mole map into the center by multiplying by the concentration of that acid. The last step is to use the molar ratio from the balanced chemical equation. We recognize for every one HNO3 that dissociates in solution, it will produce 1 mole of hydrogen ions. So we have a 1-to-1 ratio. For every 1 mole of HNO3, we have 1 mole of H positive. We do that calculation, and I get a value of 0.0105 moles of H positive. Step 3, we are now going to solve for the moles of hydroxide. A very similar monorail that we have just set up here. For the acid, we will do for the base. We have 350 milliliters of NaOH. Again, first thing we've got to do is get ourselves onto the mole map. 1,000 milliliters in 1 liter. Then we're going to move from the bottom of the mole map into the center by multiplying by the concentration. And again, because we have a strong base, we know it's going to ionize 100%. For every 1 mole of sodium hydroxide that dissolves, it's going to produce 1 mole of hydroxide ions. And I get 0.280 moles of OH. This is the point at which we have to stop and think about the 2 values that we have in front of us here. What we're saying is that we have each of these in solution. Now, we know that when you mix an acid and a base together in the same container, they are going to neutralize each other. The neutralization reaction that we have written up on the board right here shows that there's a 1-to-1 ratio all the way across. This is our molecular equation. If you remember from our previous units, if we were to write a net ionic equation for this, our net ionic equation would be H positive goes to OH, plus OH gives us H2O. In other words, H positive and OH combine together to form water, all in a 1-to-1 ratio. We're going to use that so that we can determine which one of these we have an excess amount of. It's fairly simple. You can look at the two numbers and see that the moles of hydroxide are larger. Because we have that 1-to-1 ratio of H positive to OH negative, we can just simply subtract these two values from one another. 0.280 moles of OH minus the 0.0105 moles of H positive. This means we're going to have 0.270 moles of OH negative in excess. Now, we've recognized that we've solved part of the problem. We know we're not going to have any hydrogen ions in excess. We have hydroxide ions in excess. The problem is asking us, though, what is the concentration? We need moles per liter. We've got moles, so we just need to divide that now by the total volume in the solution. So we do a side calculation here real quickly. We have total volume of our solution. We have 350 milliliters plus the 35 milliliters. Gives me 385 milliliters. I'm going to do a quick conversion. Convert 385 milliliters, 1,000 milliliters in 1 liter, and that gives me a volume of 0.385 liters. I'll take my moles, 0.270 moles of hydroxide, divided by my total volume of 0.385 liters, and that gives me a final answer of 0.688 molar OH in excess.